In the cloud, autoscaling is common. Many different types of systems autoscale. Functions as a service platforms like Lambda or Google Cloud Functions, serverless platforms like App Engine or raw VMs, all of these autoscale. And when you start learning about it, there are a lot of details you get sucked into while missing the big picture. And without the big picture, the details don't make sense. Conversely, once you understand the big picture, the details take care of themselves. You have a context into which you can put in the details. So in this video, we are going to take a step back from the details which vary from system to system, whether EC2 or Lambda or whatever, and understand the underlying principles, the elements that are common to all autoscaling systems. The first thing you need, and we'll just make notes here as we go along, the first thing you need is a metric. For example, utilization is a metric, and it keeps going up and down in this graph. It could also be latency. You need a metric that responds to your actions. The number of requests would not be a good metric, because if it increases and you scale up your system, it doesn't come down. It shouldn't be like that. It should be like the temperature in the room. When you turn up the AC, the air conditioner, the temperature goes down. It should have an inverse relationship this way. So utilization is a good example. If your utilization is high and you scale up the system, the utilization decreases. Likewise for latency. So whether it's utilization or latency, you need to pick a metric to measure. This is the thing that you're measuring to tell you whether you need to autoscale and when you need to autoscale. Then you have an upper bound, like 70%, and a lower bound. In this example, the lower bound is 90% of the upper bound. So what happens here? In this graph, as the utilization keeps fluctuating within the bounds, the system neither scales up nor scales down. And let's say the system experiences high utilization for a short while. Does the system scale up here? No, it doesn't. It doesn't overreact to temporary blips. And then the utilization comes down. So there's no scaling happening here. You don't want any auto-scaling mechanism to be oversensitive and react to tiny blips, because you'll have tiny blips all the time. An analogy is the gears in a car. You don't keep changing gears once you've reached a constant velocity. You don't typically keep changing gears every fraction of a second. It's not like the steering wheel. You keep adjusting the steering wheel all the time. It's not like that. It's more like the gears. So auto-scaling should not keep reacting continuously when the system is at steady state. And remember, even in steady state, there are blips. So coming back to this, the utilization has come down. So this is why we did not auto-scale here. This was a blip. After a while, the utilization increases and stays above the upper bound continuously for a while. Then the scaling algorithm recognizes this and says, okay, it's time to scale up. And when you scale up the system, the utilization decreases. Remember what we discussed earlier? The metric moves in the opposite direction to your actions. If you scale up, the metric goes down. And once you do that, the utilization comes back to the normal. So these are the three parameters we identified. The fourth thing we need to identify is a damping factor. This is where you tell the algorithm how long to wait before taking action. So for example, you could say, for this, measure 3 points over 3 minutes, right? So assume you have a 1 minute granularity of recording the data. So you are measuring 3 points over 3 minutes. If all are greater than 70%, scale up. So this is where you are saying, firstly, anything that's shorter than a minute, you are not even measuring data at that granularity, so it gets averaged out. Now, even over a minute, so for example, if you have three values like this, let's say 79, then 69, then 99. Even though this and this value is higher than the upper bound, which is 70% here, the system does not scale up because one of them was lower. So basically the system thinks twice before reacting. It's not overreactive. It wants to be sure. That is what happens when you do all, even if one of them is slightly lower and the others are much higher, and this is very high, even then. That's the all rule. Similarly, if all are less than 63%, scale down. So again, if you have three values, 0, let's say 64%, then 0, even then it doesn't scale down, even though these two were very low, like as low as they can be. In case of AWS Lambda, these are different. So the way AWS Lambda works is, I'll write it here. If all three of the most recent values, all 15 of the most recent values, so this number can be different from this number. So it really waits for 15 minutes before it scales down. So this is what prevents it from being very erratic and overreactive and keep going up, down, up, down. The thing is, when you scale up a system, it incurs a cost. You have to start up instances, you have to start up a VM, you have to make database connections, connect to other services like S3 or whatever, right? It has a cost. You don't want to keep randomly scaling up and down every second. So this damping factor, it says all, and all is a keyword. If it says any, then the system will be much more reactive, which you don't want. And notice that no situation can satisfy both the conditions. So suppose you had a condition like this: if any of the last three values greater than 70, scale up. If any of the last three values less than 63%, scale down. Now suppose you have these these values, 71, 60 and whatever, 65. This satisfies both the conditions. One of them is greater than 70 and one of them is less than 63. So both the scale up and scale down actions will be taken concurrently and fight with each other. So to put it graphically, you don't want these two to overlap. There needs to be a gap between the two. So in summary, when you work with different systems, there are a lot of parameters and tuning and consoles and alerts and a lot of terminology that varies from system to system. So for example, with AWS Lambda, let me tell you how it is calculated, the utilization. Suppose you have a provisioned concurrency of 10 functions, right? Now, assume your latency is 100 milliseconds, right? Which means provisioned requests are actually 100 per second, right? If you have 10 functions, each of which processes a request in 100 milliseconds, That means each function can process 10 requests per second. And since there are 10 of them, you have 100 requests provision capacity, which is 6000 per minute. Now, how many executions have happened? Let's say actual requests. Let's say there are 3000. Then the utilization is 50%. Right? Let's walk through this again. You have an AWS Lambda function. You have provisioned a concurrency of 10. The latency is 100 milliseconds, which means you have a provisioned request capacity of 100 per second or 6000 per minute. And the actual requests are only 3000 per minute, which means your utilization is 50%. This is for AWS Lambda. This is an example of details. So you need to understand these details when working with a system, but you need to understand this in context of the overall elements of autoscaling. If you'd like me to set your team up for success, my consulting link is in the description.